Most of us have experienced traveling through tunnels. It is an enclosed underground passageway or road, with the exception of the two ends, which are open. Tunnels can be used for a variety of things, including the operation of trains, metros, and roads. The ground's texture, environmental factors, and sustainability are all taken into consideration when building tunnels. Before construction, tunnels' length, width, depth, and diameter should all be considered and carefully studied. Temperature, pressure, climate change, soil quality, and other geographical conditions are also danger factors. Hello everyone, this is AWZ. Welcome to our channel. Don't forget to subscribe. Enjoy. Tunnels are one of the most important pieces of infrastructure that keep our cities moving, from underground highways to the network of tubes that make up many of the world's biggest mass transit systems and the mechanism by which we carry garbage away from urban areas. But unlike above-ground infrastructure, which after construction is finished, becomes a visible part of any city, our tunnel's size, engineering complexity, and procedures go mostly unseen by the millions of people who use them every day. The major obstacles that must be solved to make our world's tunnels a reality include digging in the dark, assuring safety, minimizing interruption, and providing fresh air beneath. Apart from a few sporadic access sites along their courses, the majority of today's tunnels are constructed using techniques that make it difficult for the general public to observe the construction of these structures. Contrarily, the original tunneling technique, known as cut and cover, was among the most upsetting procedures a city had to go through in order to build essential underground infrastructure. Engineers would use this technique by first excavating a trench, placing bricks to create the tunnel walls, backfilling the excavation, then re-establishing the surface above. With this strategy, lengthy lengths of the streets above had to be closed, which caused congestion. In certain cases, it was necessary to purchase homes along the path before work could begin. The Metropolitan line in London, the first subterranean railway route in the world, was built using the cut and cover method. The numerous track segments that have been left exposed where buildings were not restored after construction is evidence of the influence of the construction activity to create this route even today. In order to build tunnels in metropolitan locations today, tunnel boring machines, or TBMs, are used, which greatly reduces the disruption that earlier tunneling plans produced. TBMs are able to excavate material and line the tunnels that they form in one continuous process, increasing efficiency and significantly improving safety. This is similar to the tunneling shield developed by Sir Mark Isambard Brunel during the construction of the Thames Tunnel in the 19th century. TBMs must be transported to their entry locations in pieces, where they must then be lowered into access shafts and assembled because of their size, ranging from 150 to 200 meters in length. While there are numerous TBMs for various soil types, the main component that unites all of these systems is the forward-facing, rotating head that is fitted with a set of blades capable of cutting through various types of rock and clay. Conveyor belts are used to move excavation waste back towards the tunnel entrance after being funneled behind the cutter head. One of the largest infrastructure projects in the world, London's Crossrail, generated a significant amount of waste that was transported to the Thames estuary and used to establish a sizable new wetlands sanctuary. Precast concrete shells are brought in to form the tunnel lining behind the TBM as it advances, preventing the surrounding earth from relapsing into the void. Many TBMs, like those used to build the Channel Tunnel, are simply driven off into the earth and left in place once they finish their work because the costs and logistics involved with removing them are prohibitive. In recent years, however, and as a result of rising costs, a number of projects have removed their boring machines upon completion, ready for reuse on subsequent projects. While the physical construction of tunnels is a considerable engineering feat, the ongoing operation and management of these structures can be just as challenging. Regardless of their use, monitoring tunnels throughout their lifespan to ensure their ongoing safe operation is paramount. Ventilation is critical, particularly with road tunnels where high levels of pollutants including carbon monoxide and nitrogen oxide are continually discharged. Numerous methods are used to improve the quality of air in tunnels. While some systems force clean air through these underground spaces, others focus on the extraction of pollutants through ventilation ducts, which in turn draw fresh air in. The Central Artery/Tunnel Project in Boston, a plan that reroutes Interstate 93 Central Artery via the Thomas P. O'Neill Jr. Tunnel, has been modeled using SimScale. SimScale is a user-friendly cloud-based engineering simulation platform with more than 150,000 users that allows anyone to build potent, high-fidelity simulations in a web browser. The community account, which grants access to thousands of open simulations to encourage knowledge exchange and crowdsource advice, allows users to test the platform without cost. Many tunnel ventilation systems cooperate with fire suppression systems to remove smoke in the case of a fire. Road tunnels have sophisticated traffic management and signaling systems in place to lower the possibility of vehicle collisions, which could halt traffic in such a small area. Electronic displays for motor vehicles give drivers current information on which lanes are in use and warn them of impending obstacles. In order to reduce the likelihood of collisions between vehicles, changing lanes while traveling through tunnels is also typically prohibited. To avoid vehicles becoming stuck in traffic once inside, many road tunnels also have traffic control systems outside of their entrances. Metro tunnels have sensors that alert drivers to the status of other trains ahead and signals that run the length of the tunnel's route, allowing drivers to stay at a platform in the event of an incident. Emergency systems warn drivers and passengers to leave their cars and head to the closest safe haven or exit point in the unlikely event that these systems are unable to stop an accident inside the tunnel. To further lower the risk of a head-on collision, many modern tunnels are now constructed in pairs with traffic moving in just one direction. In an emergency, this method enables travelers to proceed through to the security of the backup tunnel. Although they are frequently overlooked, tunnels are in fact the lifeblood of our cities. These vital pieces of infrastructure, which run beneath our feet and carry millions of people every day, exist in a completely separate world. This is all for today. Don't forget to like the video and subscribe our channel. Stay tuned with AWZ.